Hi guys, this video defines two operations on doubly linked lists, one for adding a node and a second for removing a node. It turns out that once we define these two operations, it gets pretty easy to define all of the other doubly linked list operations. So this video is going to describe a node class, concretely the data type that represents one node in the list, and an add node before operation that adds a new node before another node that's already in the list. Finally, a remove node operation that takes one node out of the list. Here's the node class. On the right, we have a sketch of a doubly linked list. And remember that every node in a doubly linked list has a previous pointer and a next pointer and stores one element. We see those data members down here. There's a t element. T is the template parameter for the data type of one element in the list. There are also two shared pointers, one called prev or previous and the other called next. We often abbreviate previous prev so that both of these have 4 letters in the name. It keeps things tidy. Up here is a constructor that initializes the 3 data elements. And note that I chose to make the arguments go in the same order left to right as the order that we draw things in the sketch. If I look at a sketch of the one node moving left to right, first I see the previous pointer, then I see the data element 1, then I see the next pointer. And I've chosen to make the arguments over here follow that same order. First is the previous pointer, then it's the x value that goes in the node, then it's the next pointer. I find that that order just helps me visualize things. Let's get into the add node before function. It takes 2 arguments. One is where we're adding the node. So we need a pointer to a node. In the sketch here, where is pointing at a node containing 4. And we need tx, that's the value that will go in this new node, and those are the only 2 arguments we need. The purpose of this function is to add a node before the where location. So in my sketch here, if where is 4, we need to add a node before that spot, so that means a new node needs to go in between the 7 and the 4. Before we get into the details of the code, let's count pointers. I like to make a checklist like this to make sure that we don't overlook anything. So in my sketch, 7's next will need to change because there's going to be a new node in between. 7's next needs to point at that new node, so that's 1 pointer. Similarly, 4's previous will need to change to point at the new node, so that makes 2. And then we're creating a new node that itself has a next and a prev. That makes a grand total of 4 pointers. So we need to make sure that our code correctly updates 4 pointers. Now let's step through the process. First, we create a new node. It has the value x that was passed in. It's 3 in my sketch. And the previous would need to point at the 7 in the sketch, and the next would need to point at the 4. Here's how we get at those nodes. The previous of the new node should be the same thing as the previous of the where, the 7 in the sketch. So to get at that node, we follow the where pointer and then follow a previous pointer. That gets us to the node that is the previous of the new node. So that's why the first argument is where previous. And then the next pointer of the new node would be where itself, because we're inserting the new node before where. That handles 2 of the 4 pointers. Note in the sketch that where is a pointer, it's pointing to the 4 node. Also, new node is a pointer, it's pointing to the 3. There's 2 pointers left. We handle the where previous pointer next. So where's previous needs to point at the new node instead of at 7. And the way that we're getting at that is to say new nodes next. So we have 2 pointers into where. It doesn't really matter which one you pick. You could use the where or you could use new nodes next. And to make the code kind of symmetrical, we're doing new nodes next and then change your previous to point at the new node. Finally, the 4th pointer is the 7's next in the sketch. There's actually only 1 pointer at this moment. So at this moment in time, before we update 7's next, there's only one way to get at the 7 node. We can't follow where previous because that just got changed. So the only pointer we have to the 7 node is the new node's previous. New node's previous needs to change its next to be the new node, as shown in green. And that's it. That's the 4th pointer. We increment the size so that the size of the list stays up to date, and we're done. Next, let's look at the remove node operation. It's given a pointer to a node called where, and the goal of this operation is to remove that node. So the 1 node in this sketch needs to go away. Again, we're going to make a checklist of nodes that need to change. The 7's next needs to change. The 7's next will become the 4. It's going to circumvent the 1. It's going to skip over the 1. Likewise, the 4's previous needs to change. It's going to skip over the 1 in the reverse direction, so 4's previous needs to point at 7 after we finish removing the where. Also note, where is the argument passed in? It's pointing at the node to remove. That counts as a pointer as well. That's going to come into play with deleting in a moment. Now let's look at the code. We do have an exception check. You're not allowed to remove nodes when the list is empty, so we check for that first. If we get past that, we know that where is pointing at a node that's not the dummy node, which is one that can be deleted. The dummy node is never removed. Okay, so first we're going to update the pointer shown in green. We need to navigate to that node, so that would be where's previous. So where's previous gives us the node to the left of where, and then we change its next to become where's next, right? Where next gives us the node to the right of where. So it's a little bit of a tongue twister here, but that's the right thing to do. Where's previous changes its next to become where's next. That's one of the 2 pointers that needs to be updated. Now we do something that's symmetrical, kind of the reverse. So basically 4 needs to point at 7. So to get to the 4, we say where's next. That is the node to the right of where. It changes its previous to point at the 7, which is where's previous. So altogether, where's next changes its previous to become where's previous. Then that's the second pointer that needs to be updated. We decrement the size to keep the size up to date. And then there's one last detail, which is freeing this node. This needs to be freed. Now, this will happen implicitly. I don't need to write any code to do it, but I want to emphasize how this happens. We're using shared pointers. The rule for a shared pointer is that when there are 0 pointers pointing at an object, the object gets deleted automatically. At this moment in time, we're down to 1 pointer. There were 3 at the beginning. At the beginning of the function, there was the where pointer and a next and a previous pointer all pointing into 1. Now we've gone down to 0 when the function ends. So before the function ends, there's only 1 pointer left, where, the argument to the function, that's pointing at 1. 1 is hanging on by a thread just by virtue of that one last pointer. When the function ends and we get to the close brace there, the argument is destroyed. This last shared pointer where is destroyed. Now at that moment there are 0 pointers pointing into 1 and 1 gets automatically freed. So this code actually does handle freeing the 1. I just want to mention that because it's not obvious how it happens.